Welcome to session 3. So in today's session, we're going to learn about GNNs, how we can train them, and how to design GNN models. What are the building components or the building blocks and operations of a GNN layer? And at the beginning, so we're going to start with a reminder and overview of the past few lectures, what we covered so far, and we will, take a step-by-step approach into debunking the training of GCNs. So this is the first part, and the second part also we're going to expand on that a little bit, and then I'm going to give you an overview of the GNN layer operations and define a few of them. Great, so let's get started right away. If you guys remember, in the very first lecture, we introduced the particular notions and definitions that are important, including the importance of the matrix of a graph, the types of graphs, the different learning tasks towards the end, edge-based learning, we have node-based learning, we have graph-based learning. And in lecture 2, we learned about node embeddings. So how can we basically learn the embeddings of a node in a graph, and also how to embed particular graphs, for example. So node embeddings are very powerful because we're learning how to represent the graph itself, the entire graph or element of graphs in a very compact way. Okay, so representation learning is very important, and this is what we have covered. So we covered the trajectory from basically machine learning to deep learning, and ultimately to graph neural networks, particularly graph convolutional networks. Okay, so what we have seen so far is that the node embedding or the feature embedding is based on message passing. So the generalized message passing propagation rule aims to update these embeddings. So how can we update these embeddings in a GCN layer? So this is based on 2 steps. The first step is we rely on aggregating information from the node itself, or myself, and my neighbors. All right, so we take a node and we aggregate information from its neighbors. So if we do 2 layers here, so we're going to aggregate information from starting with the furthest neighbors and going all the way up to this, a particular node. Okay, so there is also the process of self-aggregation that we talked about, and we discussed different variants in lecture 2. And after aggregating, we have the second step. So the second step, we transform the aggregated representation or the aggregated embedding. So we apply a transformation that is learnable, and this is what we called omega in our mathematical formalization. So this is a learnable transformation, and we can call it also mapping. All right. So the generalized propagation rule is defined. Basically, these are the embeddings of all nodes in the graph in the layer k+1, and it is a function of the embeddings in the previous, in the layer. Okay, and it takes also as input the topology or the adjacency matrix of the graph. Okay, so the adjacency matrix of the graph. Now, we have also seen quickly the update rule. So the node embedding update rule that is based on this equation. So in this equation, we first do a self-encoding, as I mentioned. So you apply, the transformation to the embedding of the node n in layer k. Okay, and we transform it or map it through this omega k. And in this case, we have the same omega k or the same transformation applied to the node itself and its neighbors. Okay, so in the second part here, we have the aggregation of the neighbors. So after we aggregate, we add also a bias. So this bias accounts for, data shifts and shifts in features and representation. So we can, of course, get rid of the bias or include it in the omega in a compact form, as we do for support vector machines or any kind of supervised classifier or regression model. So we can simply combine the beta with the omega k in a single a matrix or a single entity, but here we separate them out and we show that we can actually account for bias in the data transformation that we have. So now after we do the aggregation, we aggregate and transform, and we have the bias, right? So we apply an activation function. So this is, the nonlinearity that we introduce. So here, so far, all this part right here is actually a linear, okay? So now this is a linear mapping or a linear combination, aggregation, and transformation of the original features of these nodes, of the nodes in the graph. But once we apply this A is actually what introduces nonlinearity into our neural network. Okay, so it's applied to all of these aggregated and transformed features. So we went over this in detail in lecture 2, and after that we generalized this to basically multiple nodes. So we can have this update rule applied to all node embeddings simultaneously. And this is a nice mathematical, equation to write, because here we can see that we can update all together. And yeah, so now after this, we looked at basically these the hops. So we talked about the receptive field and the different layers. So each layer presents basically a ring. Okay, so this is layer 2, layer 1, etc. So 1 hop neighborhood, 2 hop neighborhood, etc. So we explore neighborhoods and we expand our graph, and the nodes neighborhood defines the computation graph over which we aggregate and transform embedding. So it's called a computation graph here. So because we have basically, if we look at these neighbors, we're going to start. So this graph, let me use a different color. So this graph right here, okay, so that's not very different. So here, so this graph is the computation graph of this node. Okay, so here to update the node embedding of, here, let's say hk plus 1 of node I, right? So this is node I. We need to take into account the self-embedding and all neighbors. So this presents a computation graph over which we're going to collect, all these embeddings, right? We're going to transform them, collect them, aggregate them, transform them, and optimize them, of course. So there is an optimization process that is happening behind the scenes, and we're going to talk about this in a bit. So keep that in mind, okay? Cool. So what is the ultimate goal now? So remember, guys, we wanted to learn embeddings. We wanted to learn good embeddings for these, feature for these nodes, starting with the original feature representation. And we said that the original features may not be very good. So our goal is to learn basically these embeddings, and we hope that these learned embeddings in the final layer. So if we have big K layers, so we hope that HK in the final kth layer will be very simple and very representative. They will allow us to perform or solve downstream learning tasks, including regression and classification. Okay, cool. Now we have also seen, so let me take one step back so you guys can see that we're going backwards. So here's like a backprop to the first lecture. So in the first lecture, I have introduced the 3 different learning tasks like node classification, and we have also edge-based prediction or link prediction, and whole graph, entire graph classification or regression. Okay, so we can do supervised learning here. So in this figure, if you guys remember this figure from the first lecture, we mentioned that, okay, so we can easily use GNNs to do classification, to classify a node from using the node embeddings. And the node embeddings are here. So basically, so the question that we asked at the time is like, how do we how do we estimate or learn these node embeddings? Okay, how do we actually do that? And in lecture 2, we explained, okay, here are the rules to update the embeddings. So we looked at how to update these embeddings, all right? And then today, we will look at how we actually optimize them, okay, which is very important, because updating, if you're updating using the message passing or the message propagation, all right, using the local neighbors and all these values, then eventually you need to kind of learn all these mapping functions. You need to learn the omegas, right? And then you need to learn the beta vectors, the biases assigned like that we need to kind of co-estimate with these, with these parameters. Okay, so we have a beta here. All right, so all of these parameters, we need to kind of optimize them, right? Because, you know, like we need to learn these embeddings. So now let's look at this. If you guys remember, so this is, you know, here we have the sigmoid function that will give us the final, the label of node n. And beta here is actually, it's different from the other beta of the bias that we added for the node embeddings. This bias is the learner bias. So beta k here actually belongs to R. It's a scalar. And the omega here is the classifier or the learner, okay, parameters. Okay, so the learner parameters, for example, the classifier for using multi-layer perceptron, it's the mapping, the layer, the weights of the MLP layer that we added, that we add here. Okay, so this equation is very important because this what it actually defines is what we call here. So I'm going to move it. Let's move it a little bit up. Okay. So it defines what we call the overhead, the head of the prediction in the network. So the head of the prediction in the network. So this is a node level prediction head. So a node level prediction head, it means that once I get my embeddings, okay, so once I get my embeddings, I'm going to feed them into a response, another network, or another, you know, small network parameterized by WK and beta k. And here, these two parameters, they allow me to map this HK onto the final classifier. So this is exactly what we do in linear and nonlinear classification. So if you guys remember in the preliminaries section, this is how we formalize a typical linear or nonlinear, you know, classification problem. So we need to kind of learn these parameters, and by solving these parameters, we're going to get the final outputs. Okay. So what are the parameters to learn? So this is a very important question. So I want you guys to think about this whole network, okay, and including the prediction hat that we introduced here. And you take a minute and you try to write down all the parameters that we need to learn. Okay, so let's take a minute and think about all the learnable parameters that we need to optimize, okay, to get the final predicted label y hat of node n. And then we will compare it, of course, with the ground truth for the final evaluation. So to get this, you know, predicted output, okay, we need to optimize what exactly? So you can write them down, 1 and 2, and so you can articulate them in terms of variables or in terms of so let's look at this H and B. So very good. So we have here, first we need to optimize the embeddings, right? So we need to optimize the embeddings. So the embeddings, to optimize the embeddings, we need to basically, so let's look at this. So we need to optimize the H, right? So the H for each layer K for each layer K, right? So now to optimize this, we will mathematically, we need to look at the propagation rule. So remember, this has two different components. So we have the omega, right, 1 to omega big K, and we have also the beta 1 to big beta K, and these are here high dimensional. So yeah, so these are the two elements. So we have biases and also the parameters or the weights of the transformation, okay? So the weights. So the weights and the biases, these are for, you know, the transformation that we are applying to the embeddings, right? So we're transforming them, we're mapping them onto new subspaces, as I explained before. So we need to optimize the embeddings, and we need to optimize the learner parameters. Okay, so what are the learner parameters here? So we have two. We have the omega k or wk here, and the beta k, which is a scalar. So these are different. So this is an omega k here called, and the scalar value beta k, and this is a vector. So this is the omega k here, and we have hk, okay, k, and this will give us that this element right here, which is calculated over there. We add the bias, and then we apply the sigmoid. So you guys can see that we have loads of parameters to learn. So we have parameters here to learn for each layer. These are mapping, you know, big mappings that we're learning, a lot of weights, a lot of biases. And on top of that, we add the learner parameters, okay? So now for edge prediction, it's the same thing. So for edge prediction, how, you know, like to learn. So for the edge, sorry, let's look at this. So for the edge prediction, we have also a different head. So here, this is called the edge level prediction head. So once we learn the embeddings of two nodes, node M and node N, for example. So this is node, let's say M right here, and this is node N. And by calculating simply a similarity measure between them, between these embeddings, these learned embeddings and the final layer, okay, so here we should actually, if we want to put the final layer, we should add a K here, okay? So if we want to make that precise. And calculating the dot product tells us about, quantifies the similarity between these. So as we quantify the similarity between these two embeddings, we are able to kind of, you know, derive the existence of a link or not, or an edge. So we can apply a sigmoid function to that, and this will give us something between, you know, 0 and 1. So if it's very close to 1, it means, well, there is a link, there is an edge between these two. And if it's like close to 0, then these are not actually connected, so it's empty, okay? Cool. Now here what we have, so we have the embedding of node, you know, M, and we have the embedding of node N, and we do the dot product between them, and we get this value, apply the sigmoid and activation function, and that gives us the final you know, label that we want for this, whether 0 or 1, okay? Good. So now the next question is that we understand that we have things to optimize, right? So we have all these guys to optimize. We have the embeddings, we have the learner parameters, and we have all the transformations, omega 1 to omega k, in addition to their biases. So now the question is how to learn and optimize these parameters, okay? How do we actually learn them? So this is important. So if you have taken any machine learning course, you would know the answer. So the answer starts with a loss function. All right. So first, you know, after we design, you need to design your GCN layer. And after you design your GCN layer with its components, so we're going to see that in a bit in the other sections of this session. So right here, we're going to focus first on key components of the GCN layer. And then we need to define a loss function to optimize. And by optimizing our loss function, minimizing our loss function, we will be able to get the final optimal or suboptimal parameters, okay? Some good solutions of all these parameters that we want to optimize, okay? So first we need to define a neighborhood aggregation function, and we have seen a few, and we'll see a few more examples later about how to aggregate, because this is a very active research area in GNN. So it's an active research area. There are lots of variants and lots of alternatives, and each one of them each method has pros and cons. And learning how to aggregate is what makes basically what makes use of the graph, right? Because at the end, we're taking, a graph, and we are identifying the closest nodes, and based on these neighbors or these closest nodes, we're doing an integration or an aggregation of their embeddings, right? So without this topology, without this kind of local neighborhood, we move back to a conventional deep learning model. Okay, so this is very important. Now let's move next. So the next thing, after we define a neighborhood aggregation function, we need to define the building blocks of a GCN layer or a GNN layer. So here, by building blocks, we mean operations like how to aggregate, the linear transformation, the type of nonlinearity that we want to introduce. Is it a sigmoid, a ReLU, a max, like a 10H, for example, right? So there are different types of nonlinear activation functions that we can use. So we need to predefine that. And additionally, we can add other things or other, building blocks. So we'll learn about that later. So now next, which is the crux of this whole, learning paradigm or a graph neural network, is to define the loss. And the loss is important for, any optimization or machine learning problem, right? So we need to define our loss function. And for example, we can use here, binary multiclass cross entropy for classification, and the least squares or the mean squared error for regression. So whether you're doing classification or regression, and for classification, the output will be passed through a sigmoid or a softmax. Then we apply the cross entropy. Okay. So here in this, just a note in this section, we will examine only supervised node and graph-based classification or regression, but in a similar way, we can adapt such formalization and steps to other learning tasks. So we want such as, for example, edge prediction or unsupervised tasks. So these are easy to kind of, adapt to if you understand these fundamentals, okay? So now after we define the loss function, so here we will move next. So we need to kind of define the prediction head, okay? So the prediction head is actually connected to the loss function itself. So because we're doing graph-based learning, GNN, so you need to define your learning task. So you have either node level prediction, edge level, or graph, or you can combine all of these. So that's even higher level. But here, this prediction head will include additional hyperparameters or parameters as I explained earlier. So we have, for example, the beta and the W or omega encoding, the classifier, bias, and weights to learn. Okay, so if you want to classify, you need to add that, and this is exactly what we talked about. Where is it? So we need to zoom. Yes, right here. So this is the head, and our goal, the loss function here, if we want to use a simple loss, so let's say we can do a cross entropy loss, okay, between simply the yn predicted and the yn ground truth label, and we sum, of course, we need to normalize with respect to all training nodes, okay? So we can use a cross entropy loss here between the y hat n, and the y hat n is right here, so we can get it over there. This is our prediction by the mapping of the learned embeddings through W and beta. All right, now, so going back to this, now number 5 is optimizing the loss. So now that we have defined our loss function, okay, our prediction head that we're going to add to the GNN to take these learned embeddings and map them onto a target output like a label, a target label, or a target score for regression problems. Now we need to optimize the loss. And to optimize the loss, we're going to optimize the loss over embeddings and additional hyperparameters. So the classifier weights and biases, for example, like the learner weights, if you're doing supervised learning, and over the embeddings, okay, during the training. On the training samples, so we are going to use the training samples to optimize our loss as we do in, conventional ML. And we can usually we use, gradient descent, for example, but stochastic gradient descent regularizes better, is this better option. So we can use stochastic gradient descent, okay? So here, when optimizing, just to recall, for the optimization, we have different sub-steps, and I assume that most of you know this. So first, you need to calculate the loss during the forward pass. And then we calculate or compute the gradient of the loss using the chain rule during the backward pass. So in the forward pass, you calculate your loss, then you do your gradient, and then here you use the update gradient rule or network rule to update the parameters. So if you have your parameters, the total parameters, let's call theta, the parameter set storing the GCN, parameters, and the learner or the prediction head parameter. So all parameters will be stacked or like into a single theta vector. And here, if we have t, so this is iteration t. So if we use gradient descent, so we take the theta t minus 1 that was learned estimated in the previous iteration, and then this is just simple gradient descent, right? And then we basically subtract the learning. So this is a learning rate. So all of you must know this. Okay, so it's a learning rate. And then we have the gradient of the loss with respect to the parameters theta t minus 1. Okay, so this is the update rule, and this is simple gradient descent. Okay, so we try to kind of, if this is our loss, so let me, so let's say maybe I'll draw something different. So maybe something like this. Okay, so this is our loss. We have theta here, and if you have L of theta, right? We will start off with a first initialization, let's say theta 0 and theta 0. So that's the first iteration here. And then you're going to go down over, like down this basically loss function using gradient descent until we get to the optimal theta. Let's call it here theta star. Okay. So that's a local optimum, of course, especially if your function is non-convex or your loss is non-convex. But that's the overview or the gist of it, of gradient descent and optimization. So these first, just to summarize, these first, the first 4 elements, they are based on definitions. All right, so you need to predefine all of these or in your design, okay, of your TNN. And then you do your optimization last. Okay, cool. Now, let's take an example. I think it would be very exciting to see how this actually works. So now, in this example, we're going to look at a node multi-regression. Okay, so a multi-regression problem, a node multi-regression problem using vanilla GCN. So here I'm using this simple propagation rule that we also visited in lecture 2, but we can use any kind of propagation rule without loss of generality. This will apply to any propagation rule, but for the sake of, for simplicity, I'm using this one right here. And what we have, so this is the this is the learnable parameter. So this is the omega. I removed the bias here, but of course we can add the bias. So this is the transformation parameters or weights, okay, that we will apply to the embeddings to transform the embeddings, transformation weights. And we have, this is the adjacency matrix. So we have n by n adjacency matrix here, and is a number of samples or nodes. We have D features, so D features, so it's D by n. X stores for each sample here. X stores the initial feature vector, okay? the initialization of our embeddings, which we call H0. And then we have additionally the scores, the target scores. So each node, every node here, so node I, will have a set of C scores. Okay, so we have, it's N times C. So here we have C scores to store, which means, for example, in this graph, so here each node is annotated. It has an original measured or observed set of features that we want, of course, to transform through our network using the mappings throughout different layers, right? So that's how we want, and the aggregation rules. But additionally, each node has a set of scores. So for example, these set of scores could be different numbers. So 0.2, 0.8. So this one will have 0.7, 0.5, etc. So here we have two scores, right? So you're going to have C scores stored here, and this Y will define the vector, the feature vector, right? Sorry, the score vector for node I. Okay, so this is for node. So we can, for node I, if this is node I. Now, when we do the propagation or the message propagation, so remember, guys, we do of course, self aggregation here. So in this case, it's included in the I. This is for self aggregation, as explained in the previous lecture. And then we have 3 layers. So we have the first ring. So this is layer 1, layer 2, layer 3. And we propagate these, basically embeddings all the way down to the I right here. So this propagation rule applies, as I mentioned, aggregation, transformation, and nonlinear activation. Okay, so now we have this element new, so the multiple scores. So the goal here is to train a network using these training nodes. And then we want to test it on unseen nodes. So we're going to have a node coming in, arriving at some point. And this node will have also its, feature vectors. Okay, so it's features. It's X here, right here. So it's called, so X of node, test. Okay, so it will have its features. However, we don't have the labels. So we don't know, not the labels here, so we're doing regression, so we don't actually know the scores. So our goal is to predict these C scores, okay? Our goal is to predict the C scores for this node. So to do so, we need to train our model. We need to do all of this, okay? So here, as you guys can see, we defined the neighborhood aggregation. The building blocks is actually very simple. We only aggregate and transform. We have nonlinearity also using a function A that, for example, we can take the simple ReLU or a sigmoid nonlinearity that we apply. There are different kinds of nonlinearities we can apply. And we have a loss function that we will define now. So we need to look at our loss function. So let's move up next. So we actually reached here. Okay, so now a reminder. So what we want to do, guys, is a nonlinear multi-regression. So nonlinear because we have, if you remember in the review notes, we call this F, right? So these are transformed features. So our GNN or GCN layer created transformed features in a new space or in a ultimate space. And this is what we call the embeddings, the final embeddings, right? So in layer K, this is the final layer. So now in this final layer, what we need to kind of use these embeddings to optimize a loss function. So let's say we define a loss here. So let's take it one step at a time. So we define a loss function. This loss function minimizes the squared distance between the transformed features and the target score. So this is exactly a typical or conventional formalization of a multi-regression model. Okay, so we haven't changed anything here. The only thing that we did is we plugged in the learned embeddings in the final layer of the GCN model. Okay, So HK goes in here, and this is how we calculate HK using the propagation rule, right? And you can trace it backwards to the very first, so you're going to have an A at multiple transformations and guided by the topology of the graph, guided by the topology, and parameterized by different layer-wise or layer-specific transformations all the way up to k minus 1. Okay, so this HK requires the learning of all of these omegas, right? All of these mappings. And here, basically, what we are doing is like we're taking the regression model. So this is the regression model transformation, the W, and the W has this dimensionality. So let's start from the beginning. So we have here HK belongs to n times dk. N is the number of nodes, right, in our graph. And then we have the final embeddings, and the embeddings have dimensionality dk. So this is a dimensionality of an embedding, okay, and the final layer. So it will have dk elements or dk values here. And then on the other hand, we have our multilinear mapping function, okay, regression matrix, where for each, of these basically vectors, we are mapping, as I explained before. So through this multiplication, we're mapping, all of these nodes onto a particular, score. So we're predicting the score for each of these nodes through a shared mapping. So this is a shared mapping for score 1. So we have one score here, and we have C scores. And by doing this multiplication, so the first one will get us this predicted value, right? And then for the first score, and then if we do for the last score, so we take this one again, and we multiply it by the last score, we're going to get this element, right? So we're predicting the y hat. So we're predicting for each node, okay? So let's do it. For each node, we are predicting its target scores, y hat, okay? So this gives us eventually a final matrix, and this final matrix here, we will have n times C, so n times C matrix. And in this n times C matrix, we will store all the predicted scores for all nodes in the training graph. So we're actually predicting all these values, okay? So right here for this particular graph. Now, let's look at this again. So here, what do we have? We have the predicted scores. So we do the mapping, we get the predicted scores, and we compare them against the ground truth. So as we compare them against the ground truth, this will define our actually loss function. So here, y hat, this is y hat, and our L of theta is defined like this. So y hat, the matrix, okay, minus the ground truth scores, and this is, we're going to minimize this over theta, okay? So the theta stores all network parameters. So what are the parameters here? So if we write them down, we're going to have the W, of course. So here we have this matrix, and we will have, so that's the prediction hat, right? And the learner parameters plus others, okay, other parameters of the GNN. So this is for the learner prediction hat. And we're going to have a set of parameters for the network, the GNN parameters. And using this propagation rule, we only have omegas, okay? So we simplified things. So we're going to put all of them here. So from omega 1, omega 2, all the way down to the final here, transformation k minus 1, that will map, layer k minus 1, the features in layer k minus 1 over the embeddings to the embeddings in the kth layer, okay? So we generate HK, and this is how we get our input features to the multi-regression model that we have right here. So you guys can see, so things are simple. They look simple, but the theta here is huge, okay? So it's a huge optimization space that we have. So basically, to get this HK, we need to optimize all the mappings from layer to layer, from rank to rank in the graph. And additionally, we need to optimize the regression, kind of transformation. So it's a lot of parameters. And this is why graph neural networks or deep learning are very heavy to train, because you have all these, high dimensional parameters that you want to optimize. And here you have dk times c. You'll have different dimensions for each of the omega, right, for your transformations. So we have multiple parameters to optimize. Now, once we get the theta star, the optimal parameter, right? So after the optimization, we will be able to, we're going to get all these, hats optimized, final ones, okay? Or maybe it's better to say if they are optimal. We're going to put a star for the optimal, right? And that's how we will actually calculate the HK here. So we're going to get the embeddings. Everything will be expressed and calculated in the network, okay? Now, we ticked multiple boxes. So let's look back. So we have defined all of these, the loss. And now the last step is the optimization. So we're going to look at the final step. Now we defined our loss function. We formalized our problem. We define our propagation rule. We define our layer operations. And we formalize everything mathematically beautifully. And now we need to optimize our loss. So our goal is to actually do this minimization and to optimize theta. So how are we going to optimize theta? Now we've come to the final step of the training of a GNN model, which is the optimization. So in the optimization, we will use, for example, gradient descent or stochastic gradient descent. And what I want you to do here, guys, is to take a minute to think about this. I want you to actually imagine this. All right. So I want you to kind of simulate this in your brain. What is actually happening here? What is learnable? What is fixed? What are the update rules? So I want you to kind of simulate the changes that happen to this graph. Okay, right here. And this one. Okay, so this, this is, basically here we're going to plot the two scores. So we will assume that we have two scores. So C will be equal to 2. So we have two target outputs of the network in our multilinear regression problem. So we have the optimizer iterations. So here I'm going to keep it simple. So I'm not going to go into details and talk about epochs and stuff like that. So I'm going to simplify things. And we're going to talk about these later on, more advanced kind of tools that we will use. But right here, we have our gradient descent rule, very simple. We have the parameters. We want to update the parameters and get the theta here, t. And this update rule, we're going to use it starting with t, the first iteration to the final iteration, big T right here. And this is when we have, kind of, the optimum, hopefully, theta star. Okay, so we're going to stop there and our loss has converged. So usually when you have a loss function, remember, so if we plot the L of theta, okay, and these are the number of iterations. So if I zoom here a little bit, so we're going to have something like this. So the loss at the beginning, when we have a theta, first, like theta 0, we'll have a very large loss, and somehow, as we optimize, the loss will start to stabilize. And you can see here that the loss is stable, so we can actually stop the optimization. So it's not moving anymore, and then different ways of stopping this. So so they're very simple actually. So you can set the number of iterations, or if the change in the loss is not big anymore, which means it's stable, right? So the gradient is flat here. So like you don't have any changes in your loss, so then you can stop, right, your optimizer. So this is, in terms of optimization. So let's do the simulation here. So there is a beautiful reminder I want you to recall from also the previous lectures. So what we have seen in lecture 2 is that through the optimization, we aim to find an ultimate low dimensional representation space. So this ultimate space, is a much simpler manifold. Like linear models can work well on the final embedding. Okay, so which means when we have our final embedding HK, when we apply a linear multi-regression model, things should work there. Okay, so a linear model will fit the data nicely compared to the original data, which is highly nonlinear and complex. Okay, so this is basically in this space. So this kind of influences or expresses what should be happening in this space as we optimize. Okay. Now, the second thing I want you to think about what happens to the graph itself. What is learnable and what is fixed? So let's take a few minutes here, guys. So I'm going to pause and I want you to make a drawing and simulate this and think about these values. So let me explain here one more thing. So these are the predicted values. Okay. So here, this is the Y, for example, for the first Y for node I. Okay, so it's called for node I. This is the Y hat, and then we have the ground truth for node I. So this is ground truth, and this is prediction, okay, by the network. So every time the network will predict Y be this, basically, okay, based on the embeddings that we're learning, based on two hyperparameters that we're optimizing, two big ones. I mean, there are lots of hyperparameters, but mainly the W and the omegas that control the HK. All right, cool. So let's take here just a few minutes, and I would like you to simulate this and make drawings and imagine the changes in the values, what happens in the predictions here when we start off, and what happens to other stuff, right? So what is actually being updated and what is fixed in all of these elements, all right? And then you can also make a drawing here of an initial distribution of the data. So this is the input, right? And then we have the output right here as the y-axis. And I want you to make a drawing, okay, that shows what is actually happening. So okay, so let's imagine together. So first, I would like to remind you guys that each vector here represents the embedding, the learned embedding, and the final layer, layer K, of node I, for example. Okay, so we have node I here, all right? Now let's start from the beginning. First, if we look at these embeddings at the very first iteration, so we will randomly initialize this. So that's the first thing. So let's take one step back. So first, let me ask a question. So here, what is learnable and what is fixed? So number one, the fixed elements, what is fixed? The fixed elements include the A, which means this graph, okay? These edges right here, they are fixed, they do not move. Also, the Y ground truth, okay? It's also fixed. So these two are fixed here. So what is moving, what is dynamic about this network is the embeddings, okay? So we are learning the embeddings, okay? Of course, here we're gonna have the X at the beginning, so I'm not showing the first layer, so X is equal to H0, right? So, oops. Sorry, so yeah, so H is equal to H0. It will be included, but here I'm not showing it because I wanted to focus on the final layer. Why I'm focusing on the representation or the embeddings learned in the final layer, because we're going to use these to do the regression, right? For to input into the prediction head. All right. Now the embeddings are learnable. So this is learnable. So we need to update this. These need to be updated. Also, the predictions, they are learnable, so they need to get updated. So let's start with from the beginning. So let's say, for example, the ground truth here, I'm going to put two values. I'm going to put here, for example, 1, 5, 2, 3, and 6, 5. Okay, so I'm going to repeat this, 1, 5. Oops. So these are the ground truth values. So we have two values, okay? 2, 3, and then we have 6, 5. And we want to predict these, okay? So we want to predict these values by optimizing the model over the embeddings and all the parameters on the training set. So these blue nodes, all of these are our training nodes, okay? So we have here training nodes, and these are our training nodes. All right, now for the embeddings, because they are learnable, we need to kind of initialize, right? So we need to do some initialization. And to initialize them, we need to initialize, of course, omega 1 to omega k minus 1. Okay, so all of these need to get randomly initialized, or there are different ways. So it's a big research topic, but let's say we randomly set the values of the omegas that will give us the k, the final k, through the propagation rule, right? So if you remember, through the propagation rule, we're going to get this final hk. So here we need to initialize all of these omegas. So after we initialize them, we're going to have values right here. So we're going to have some, you know, kind of different values, all right, of our embeddings for each node. And these are random values, right? So somehow, because at the beginning, the network is not learning anything, the omegas, these mappings, these feature transformations or embedding transformations that completely random, okay? So they're not going to give you something you're going to be happy with. So when we plot the values, when we project these vectors, so now we're going to do some projection here. So let's take different colors. So we're going to take this color, okay? So here, when we project these vectors onto this space and show the relationship with respect to y. So let's say, you know, each sample here will have different values, okay? And we're going to have maybe something like this. So this is, you know, I don't know, something really funky. So the first embedding will not maybe make sense. So this is one single score. And if you have a different score, of course, you're going to have, you know, a very interesting relationship with respect to that score. So here, let's say we have, you know, a single score and we want to plot these embeddings. So in the beginning, you're going to see something a bit funky, a bit random, maybe unstructured. So I should maybe make it a bit more kind of spread out. So, oops, I changed color. I should not change color. So here, yeah, so something like that. So something that is not very reasonable, okay? So these embeddings are not good because they are generated by a random transformation. Although we are using, remember, we are using the graph structure to do the aggregation, right, based on neighbors. The graph structure may be good and it is fixed, so it's not random here. Still, the transformation of these embeddings is random. So we're going to have something completely random. And then as we optimize, things will start to make sense. So first, let's look at the second variable. What happens to our y here? So first, we're going to have a very large error. So if we do, so let me redraw this, okay? So here we want to put our loss function. So like here, so this is our loss. And at the beginning, our loss function of theta, the first theta, if we have the first, you know, theta 0, right, we're gonna have really a very high loss. So everything is messed up. It means like we're not predicting well. So we may have 7 here, we may have 8 there, 1, 5, you know, 2, 3. So the error will be very large because the distance between the predicted vector and the ground truth one will be very high. So your loss is very high here. And as you optimize your theta, so you're going to start from, you know, like kind of theta 0, and then you're going to move down and you're going to have, you know, as you iterate, you're going to have a better theta at some point t, right? So you're going to have, you know, a decreased loss right here. So this loss is very nicely decreased. And you can see that somehow you started over this optimization, right? You started to get very good values. So hopefully at the end of your iteration where your loss stabilizes and you have your theta big T, so after T iterations, your HK right here will kind of have a very good representation of your data. So it will transform your complex data. So let's say the original data that we had maybe looked like this. So if we plot the H 0, which is here ground truth, right? So the H0 is the X. So let's do that using different colors right here. So I want you to imagine this too, okay? So the original data maybe has something like this. Okay, so here, this is the original data. And when I say original data, it means we plotted here H0, which is equal to X, the original features, right? The original embeddings. So we can easily kind of, maybe have a nonlinear model fit to this, right? However, we want to transform. Remember, our goal is to transform everything onto a new representation space where we use the new representations or the new embeddings where linear models can work. So using HK, what do we expect here? We expect that these embeddings now, so I'm going to use the same color, HK, after optimizing the model, at this stage, we have a very good representation there. So basically, when we plot the embeddings of the final layer of all our training nodes, okay, these are the training nodes, right? And we predict a particular score. Now we can easily fit a linear model. And this linear model right here, this linear model is parameterized by the matrix W that we have here. Okay, so that's our matrix W that that fits in the data. It's our regression model. And if we have, of course, multiple scores, we can add other scores as illustrated in the preliminary lecture. So it's not too difficult to do. So you can imagine you have a second score with different distribution. And now if we're going to write the values, so what kind of values we'll have here? Hopefully, if we optimize and we got a good, optimization of our loss function and a good estimation of our parameters, theta star for t, the final iteration t, then we're going to have very good predictions. So the predicted value here versus the ground truth should be very close. So maybe we'll have a 0.8, we'll have a 4 here, we'll have, I don't know, maybe 2.1, 3.5, 6, well, maybe 9 here. We made a big error here somehow for some reason. We need to understand and debunk, basically diagnose the training, why we made these errors, okay? Good. So this is the overview, and I hope it is kind of clear. And there was a lot of background music, I would say, that we cannot hear here. The optimizer for me is like a conductor, right? Like it's not just, it's the conductor that kind of manages all this kind of orchestra. The orchestra is basically all these players, all these neurons that trying to kind of get out the right tone. Get out the right tone, it means optimize the right W. For each neuron, we want to get the right weight, right? The very optimal weight. And imagine all these neurons, each one of them getting a note out. And this note, if you combine all of these together, right, you're gonna get the final tone or melody that you want, the perfect one that is very close to your ground truth, right? So your optimizer is like a conductor, and you have the composer, which is, all these neurons that are trying to compose their own tones and optimize their parameters. And it's a huge orchestra if you think about it, because you have millions of parameters and thousands and sometimes thousands and thousands of neurons that are trying to fine-tune and get the right activation and the right value for you to be able to finally get this simple vector out here. Isn't that amazing, right? So yeah, so that's how we do optimization here. And now let's go back to this table. So basically we optimize the loss. Now we got our theta star, right, after several iterations, training on minimizing the error over the training sample. So here it's the Y train minus the Y hat train. Okay, so of course we're using the data set, and then we're gonna compute the so we did all of these updates, and now we need to do the testing. Okay, so we need to test. So the next step will be to test our network. So let me remove this from here. Actually, maybe keep it over there. So it's just for the notes. Okay, let's keep it. All right, so testing now. Here is a question for you guys. How do we do the testing? So here we have basically a new node coming in. So this is a new node. We want to predict for this new node, okay? So a new node arrives and we want to predict its target scores, okay? So it's a multi-regression problem. Have multiple scores. We have C-scores to predict here. And these C-scores, now the testing node comes with its X test, which is the feature, the original features, right? X test. So we have the feature, we have, you know, the node itself, and we have the scores are missing. So we need to predict the scores. Now the key question here, the first thing, because the node will come isolated. So it will have its own kind of, you know, not embedding, original feature, and it will be isolated from this. So one idea is to try to connect the testing node to other nodes, okay? So we can use, for example, the dot product or a similarity measure to connect it and see that, well, based on the closest, you know, we select the k nearest neighbors, okay? So here we connect it to 2 nodes, and you can, or we have a threshold maybe. So we need a strategy to connect the node. So we connected the node, and you can see that we added it to our graph, right? Now, the question here is, how can we predict the scores of the node? Remember, guys, the prediction head. So I want you to, you know, just take a minute and think about it. If you have taken notes, or you can go back and check, you know, the beginning of this video and see all the equations that we've written down. Hopefully you're taking notes, and you should be able to derive that by yourself, okay, without me revealing the results to you, or the next step. So here I gave you a hint. So we can connect, let's say we connected the node, and then what we want to do is we want to predict the y. So how can we do that? Now that we have trained our network, we have learned all the parameters, we have learned the theta, so we have our theta star that has the, you know, the set of omega 1 to omega k minus 1, and then also the multilinear regression matrix, all of these optimized. How can we do the prediction? So let's take a minute. I want you to kind of pause and take a minute and think about this and write it down. So here first, after connecting the node, let's look at the solution. So it's actually very simple. So the first step is a forward pass through the GCN layers and the prediction head. So first we need to forward pass or pass the original features. So the original features are these guys, okay? So the features of the test node. So we take its feature vector and we pass it through the GCN layers, which means the omega mappings, right? To get the final embedding of the testing node. So this is what we call the inductive node embedding. So it's we're inducing the node embedding, we're inferring the node embedding, and we pass the original x0, right, of test through all the optimized, you know, network mappings, right? In this case, using the simple naive GCN, right, model, k minus 1, and then this will give us the hk for the test node, right? So we're going to get the embedding of the test node. And once we get the embedding of the test node, so this is the test node, okay? So this is the test node, and we have its embedding, right? We're going to simply map it or project it using the W. So this will give us, you know, the W star here, the optimized multi-regression mapping, right? And then when we do this multiplication, we will get simply our predicted scores right here. So we get our predicted. So here we pass it through the final MLP layer, or the prediction / our right. If we do MLP or multi-layer perceptron, or the prediction head to be more accurate, okay? The prediction head. Okay, good. Now we get the predicted values right here. So these are the predicted values y hat for node test. Okay, so it's a vector and it has, C values. So C outputs or C output scores, I would say output scores. And we hope that these will be close to the ground truth. So this is, the ground truth. So now we reveal the ground truth because we want to evaluate the model. So after we predict, we need to evaluate. And to evaluate, we can simply calculate the MSE, either the MAE, the mean absolute error. So the mean absolute error would be, y minus y hat for node, for example, the testing node I. Okay, so we take a simple difference here, or we take the mean squared error where we square this. Okay, great. So these two different evaluation measures that we can use to evaluate the quality of our prediction. And if we do very well at predicting, the values right here. So now we can look at the ground truth that we have and we compare our prediction and we see we can then evaluate, okay? We can evaluate the generalizability of our model, our GNN model, okay, to unseen data points. Okay, so the data points here are actually nodes. All right, cool. Now, I'm gonna ask you a question also, another question before we hit the second part, but I'm gonna leave you with this and then we will hit the second part.